In this problem, we are presented with a waveform trace of current flowing through an inductor. We are then looking for the voltage, power, and stored energy associated with that inductance. Important concepts we'll need include the inductor voltage, which is L times the time rate of change of current, the inductor power, which is the product of its voltage and current, and the stored energy associated with the inductor, which is 1/2 inductance times the square of current. Let's review the approach we'll follow for this problem. We are presented with a waveform trace of the current flowing through a 2 Henry inductor. We see that it starts at 0, climbs linearly up to 3 amps, drops back down to 0, and then goes down to -3 amps, which really just tells us that the current has reversed direction. So it actually reaches the same magnitude of 3 amps again. You see it goes back to 0 and then stays at 0 for some time. We are looking for a sketch, or actually sketches, of the voltage, power, and stored energy associated with this current through the inductance. Well, I'll start out by visualizing the inductor itself. Of course, the inductor is a 2-terminal element. We are given this current I of t and the associated voltage V of t for this inductance with value L has a polarity such that the current enters the positively labeled terminal. And this labeling scheme is compatible with the passive reference configuration. Now we know that the voltage is inductance times the time rate of change of current. Now here we see the current is changing in a linear fashion, so its time rate of change would be 3 amps in 0.1 seconds. So that's the time rate of change with units of amps per second. So we know that a linear change like this has a constant rate of change. So another way of stating this is the derivative of these straight line segments would be a constant. Now to determine the power, once we have the voltage and current established, we simply take the product of those two. Current is given, voltage is something that we find. The stored energy is 1/2 the inductance times the square of the current. Now when we square the current, we see that we have one section of the current that's positive and another section of the current that's negative. So the negative portion becomes positive when squared. And it's useful to remember that the stored energy is always positive or 0, never negative. Now let's move on to the details. The inductance is 2 Henries. We have voltage and current labeled according to the passive reference configuration. And from this we write that the inductor voltage is the inductance times di dt, or times the derivative of current. Now in this section of the current waveform, we see that we have a rise of 3 amps divided by a run of 0.1 seconds. So we say the slope of that straight line segment is 30 amps per second. Now that tells us that during this first interval we have 2 times 30 amps per second, or 60 volts. During this interval, the slope is 3, or we could say it has a rise of -3 amps divided by a run of 0.1 seconds again. Or we say now that we have a time rate of change of minus 30 amps per second. In this last section, the slope is the same, 30 amps per second. And here we would have 0 amps per second. Now that we have all of these various slopes established, we can calibrate the plot for voltage with a maximum value of 60 volts and a minimum value of minus 60 volts. Now in this region we have a constant 60 volts. During this interval from 0.1 to 0.3 seconds we have minus 60 volts. Back in this region we have back to 60 volts. And then here we have a change that tells us we have 0 volts. So we have these abrupt changes between these various constant voltages of 60 and minus 60 volts. Now, power is the product of voltage and current. So I'll do this by simply taking the product of these two waveform traces. And this axis is power, which has units of watts. Now at the beginning, the power is 0 because the current is 0. It hits a peak of 3 amps here, which gives us a peak power of 180 watts. And it follows that straight line progression of current. Now here we have an abrupt change to minus 60 volts, but the current is still at 3 amps. So we abruptly change the power to minus 180 watts. Now in this time interval, we see that the voltage is constant, but the current is declining towards 0. That means the power would move towards 0. Here the voltage is still minus 60, but now since the current is negative, those negative signs cancel, and we see the power continues to climb up to a value of positive 180 watts. Here we've got 60 volts times a negative current, so we abruptly jump back negative again, and we end up back at 0. And then after that we have 0 times 0, and the power of course would be 0 from that point onward. Let's reflect on this for just a moment. Anytime we have positive power, the inductor is absorbing energy. So during this interval it's delivering energy when the power is negative. Alright, lastly we are looking for the stored energy, which is 1/2 inductance times the square of current. And that's 2. And we'll multiply that by the square of the given current waveform. Effectively, it's just the square of the current, but of course it has units of joules. Alright, we really need to just focus back here. 3 squared gives us 9 joules. We start with a value of 0, and we work our way up to a peak value of 9 joules right here. Now when you square this constantly increasing section here, you actually get a parabolic curve as a result. And in a similar way we have a parabolic section declining back towards 0. Now during this section it's increasing again, but we're squaring the current, so that means that the negative value gets flipped positive again. And we decline back towards 0 and stay at 0 for some time. So we see that while we are absorbing energy, the stored energy increases. When we deliver energy, then we see that the stored energy decreases back towards 0. Also, it's important to realize that the stored energy is always 0 or positive. And also note that the stored energy is always continuous. An inductor's voltage can change abruptly, as can its power, but its stored energy has to be a continuous function. Well, let's summarize the problem-solving approach we used for this problem. First, we determine the slope of the inductor current waveform. This is the time rate of change, or derivative, of current. We then plotted the voltage as inductance times the derivative of the current, and then plotted power as the product of the inductor voltage and current. Lastly, we plotted the stored energy as 1/2 the inductance times the square of the current. That wraps it up for this inductor problem.